Hi, first period. So today I'm going to have you watch this video on me going through the back side of your note guide. And then the sub is going to hand out your practice, your check your understanding worksheet for 6-1. And then I want you working on that together in class and then finishing whatever you need to at home. So you guys did some of these graphing examples on the whiteboard yesterday. I'm just going to walk through a different one on your note guide so you have something to refer back to when you're doing the practice. So the first thing I want to point out when you're graphing these is that you need to take a moment and identify what your base is. Because remember, the general like AHK form of an exponential function also includes a b, and that b will change from equation to equation. So I tend to sort of highlight this or just in my mind kind of really focus in on that part. This is telling me that my base is 0.2. Some of you may be more comfortable working with decimals, some of you with fractions, so we can also think of 0.2 as just 2/10 because it's in the tenths place, and then that reduces to 1/5. So 0.2 and 1/5 are the same number. And for the table of values, I think I'm going to use the fraction because then it's easier to raise to a negative power. Because that's what I'm going to have to do. I'm going to have to take this part and first get a table of values for just that, for just 1/5, aka 0.2, to the x. So this is what we would call like the parent table of values. And I'm going to use my -2, -1, 0, 1, 2, so I can get negatives, 0, and positives, and just raise 1/5 to those powers. So when you're raising a number to a negative, remember to flip the base and then turn the power to a positive. So 5 squared is 25. And then 1/5 to the -1 becomes 5, reciprocal of 1/5, to the first power, which is just 5. Anything to the 0 power, including 1/5, is 1. 1/5 to the first power is just itself, and 1/5 squared would be 1 squared over 5 squared, which is 1 over 25. Now, this value is kind of large right here, so I probably won't use that on my graph. I know that it's part of the range. It's large, so I probably won't use this point to get my new points. I'm going to just kind of use these here. So these are my parent x values, and then these here are my parent y values. And then that's where a, h, and k come in. So a is 3. It's the number multiplying outside of the base to the power of x. And then h is this number in here, opposite sign though, so h is -3 because there was a +3 adding to x in the equation. And then you may notice that there's no k, so k is 0. Which, by the way, that means that is where our horizontal asymptote is going to go. The horizontal asymptote is based off of the k value, so that would be anything adding after the equation, and there is nothing. So y is going to approach 0 at the ends of this graph. Okay, so now I take my a value of 3, and I'm going to multiply all of my parent function y values by 3. So that's these guys. These guys are going to get multiplied by 3. Then I'm going to take all my parent function x values and subtract 3 from those. So like all of these are going to be subtracted by 3. So that ends up creating a new table of values. So I do -1 minus 3 is -4, and then -3, 1 minus 3 is -2, 2 minus 3 is -1. So these are my values there. And then I'm going to multiply each of these by 3, so I get 15. That's 3 times 5. 3 times 1 is 3. 3 times 1/5 is 3/5. 3 times 1 over 25 is 3 over 25. Okay, so I'm going to plot these new points on my graph. So this would be -4, 15. 11, 12, 13, 14, 15. So it's off the grid, but it's manageable. Way up there. And then I'm going to also plot negative 3, 3. I will also plot negative 2 and 3/5. And then negative 1 and 3/25, which is even smaller, a lot smaller than 3/5, so closer to 0. But we knew that it was going to flatten to 0 anyway because k was 0. And then I just follow that pattern. I use what I know about the parent function, that it's never going to cross 0. It's going to flatten out at this value to be able to add those arrows in. Okay, so there is my graph of this equation here. So I want you to notice that the base, the 0.2, right, that's less than 1. So my graph is what we would say decreasing as x moves to the right. That's traditional for functions that have a base that's less than 1. So let's write that down here. The transformations were 1, there was a vertical stretch by a factor of 3. And that's because the a value was 3. And that was multiplying or stretching the y value. The second thing that happened is the graph moved to the left 3 units. And that was because our h value was negative 3. And so we ended up with the graph slightly off center, right? So the left of the y-axis, where normally it's on the y-axis, and then really tall and dropping really fast because of that vertical stretch. We also noticed that our horizontal asymptote was at y equals 0. I'm just going to put parentheses. That was because our k value was 0. And that is indicated by this dotted line on our graph. Make sure you dot in your horizontal asymptotes. That also determines our range. So the y values cannot cross over that horizontal asymptote. So in this case, since a was positive, the y values have to remain above 0. So again, that's because the y's have to remain above the k value when a is positive, which it is in this case. The domain is always, and including for this one, is always all real numbers because I can plug in any exponent I want into the x. This function is decreasing because the base was less than 1, and it's decreasing the entire time across the whole x-axis. So it decreases from negative infinity to infinity. This graph doesn't have an x-intercept, but some of them do when we start moving them around. So stay tuned. We will not be able to find x-intercepts until we learn about something called logarithms. So that's coming. For right now, we can't find it yet. The y-intercept, on the other hand, is easy. We just plug in 0 in place of x in our equation. And so here's our equation up here. I would just plug 0 right in that spot where x is. And then I would have to do 3 times 0.2 raised to the 3rd power. So you can either keep it as 0.2 right here, or you can think of it as 1/5. If you leave it as 0.2, then you can just think of this as 2 cubed, which is 8. But I have 1 decimal place here, and when you cube that, you'll end up with 3 decimal places. So you can think of this as, follow me over here, 3 times 0.008. 8 would be in the 3rd decimal place. And then 3 times 8, that's just 24. But because I have 3 decimal places in this number, then my answer needs to have 3 decimal places. So it would just be 0.024. So that right there is the value of our y-intercept. You'll notice it's very small. It's a very small positive because our y-intercept is like right there, which is really, really close to 0. So this actually matches with our graph. But we would write it like this, 0, 0.024. That's if you are leaving the decimal as a decimal. The other option would be to think of it as a fraction, which would be 1/5. So whatever you're comfortable with. 1/5, if you cube it, just ends up being 1 cubed over 5 cubed, which is 125. And then 3 times 1 over 125 is just 3 over 125. And these numbers are equal to each other. So you can evaluate that in whatever way is most comfortable for you. But the main point of that is to get a y-intercept, you plug in 0 where the x is in the equation, right here, and then you just go from there. So then that brings us to example 2. And the reason why I put example 2 on here is because I want you to realize you don't need to see the graph to be able to determine the defining characteristics. For example, I can see that this function is exponential. And I know that exponential functions have a domain of all real numbers. I also can just tell by looking at the equation, I can plug in any kind of number I want. There's no limit to what kind of number I plug in. And so that means that your input can be anything. That's what all real numbers basically represents. It represents positives, negatives, zeros, fractions, square roots, pies. You can plug any kind of real number you want in here and you would be able to get a y value. Maybe not the prettiest y value, but a y value. So domain for any exponential function is all real numbers. The other thing I can tell is that this has a k value of 5. So I know right away that I'm going to have a horizontal asymptote at y equals 5, just from looking at the k value. This function has a base that's greater than 1. So I know it's going to go up and to the right like this, and on the left it's going to flatten out at that value of y equals 5 because of the k value, and that it's shifting the graph up 5. That also lets me know what the range is. If my graph is going to be shooting up and to the right and then flattening out toward 5 on the left, that means it's never going below 5. So my y value is going to be greater than 5, again, because this is an exponential function, which is always a positive, plus 5. So the lowest it can get would be like above 5. Let's see what else. Oh, I can find the y-intercept because I can just plug in 0 for x. So then that would turn into 2 to the power of -1, which is 1/2. 1/2 plus 5 is 5 1/2. So that would be my y-intercept. Again, I can tell just by using the equation. So I got domain, range, y-intercept, horizontal asymptote. I know that it's a one-to-one function because it's exponential. Oh, and I also know because the base is greater than 1 that the function will be increasing. So I know that the direction it would be going in would be up as x goes to the right. So like for the whole entire x-axis, this function will be increasing. And that again is based on the fact that the base in my equation is greater than 1. And that's it. Like those are the defining characteristics. So I just wanted to point out that you can tell a lot about a function just by looking at, in the case of an exponential, looking at the size of the base and then your k value. Then lastly, we come to example 3, which is given the graph of the exponential function, let's see if we can write the equation. Now, this type of equation will be more challenging, I have to admit, than the other ones because of the fact that we're going to have to write our equation in this form. So it's going to be a times some base to the power of x minus h plus k. So there are literally 4 things that we have to find. We need to know what a is, what b is, what h is, and what k is. Also, unlike the other graphs we've done, h and k is not an actual point on the graph. So like for example, let me go back up here to our graph from example 1. H and k for this was -3 and 0. That was our h and k. -3, 0, 1, 2, 3 is right here. That was hk for this graph. It was this point on the asymptote that was kind of directly below that point, the -3, 3. So So yeah, so it's not like I can just go, oh, here's the vertex, that's HK and whatever. I instead have to, usually what I do is I go to the asymptote and I look for kind of what the middle might be. Here's the thing though, you can get multiple answers that actually are the same, like when you simplify them. So some of you might choose to use this point as HK, some of you might choose to use that point as HK. Either one is fine. Your equation would look different, but actually would simplify out to be the same. For this lesson, I'm going to go ahead and use this point right here. It's on my asymptote. So that is one thing about HK. HK is a point on the asymptote. And it's got to be directly below one of the other points on the graph. Okay, so I had a point right here that was at 0, 1, and so I chose to put my HK directly below it. So that is going to have to be a choice, and I hope that you're comfortable making that choice. So I'm going to put my HK at 0, -2, which would make H0 and K -2. So that could eliminate that variable and that variable, but you'll notice I still have 2 more I have to solve for, which is why I have like 2 other points in my graph so that I could figure out, actually I have 3 other points. I can use multiple points to find both A and B. So I'm going to start by first plugging in the H and K that I decided. So H is 0, K is -2. So I plug those in. So then that turns into A times B to the X minus 2. Now, I'm going to use this point to solve for A. The reason I choose this point is because this is where X is 0. I need X to be 0 to be able to find A, since I don't even know what B is yet. So what I'm going to do is I'm going to plug in 0 for X and 1 for Y in my equation temporarily to see if I can find A. So I get 1 is equal to A times B to the power of 0 minus 2. B to the power of 0 equals 1. So I get 1 equals A times 1 and then minus 2. So then I would add 2 to the other side. So then I get 3. A is 3. Okay, so now here's what I have. Sorry, follow me down here. Now I have Y equals 3 times B to the X and then minus 2. So this is what I have so far. Now I can go ahead and find B. And so to do that, I'm going to have to use one of the other points on the graph. And I think I'll use this one. This is where X is 1 and Y is 7. So what I will do is I'll plug in 1 right there for X and 7 for Y. And then I get 7 equals 3 times B to the power of 1 minus 2. So I'm going to add the 2 to the 7. I get 9. 9 equals 3 times B, because it was B to the first is B. So I divide by 3. So then B is also 3. So then so now I know everything. I know A is 3, I know B is 3, and I have H and K as well from allowing it to be this point that was on the asymptote and directly below this point right here. Because remember, the reason that I realized I can do that is because that's where H and K always ends up. It always ends up directly below one of the points on our graph, but on the asymptote. Okay, so I now have all the things. I can put everything back together again. So my equation would now be, here's my A value, so that's 3. Here's my B value, and that's another 3. I'm raising that to the power of X, and then minusing 2. So here is one sample for the equation for this graph. I won't go into details about how, but maybe I'll just point out this A is to the first power and these bases match. So another possibility would be Y equals 3 to the power of X plus 1 minus 2. If you wrote this equation, this would have been if h and k was -1, -2, and in that scenario, a is 1 and b is 3. That would have been if you had used this point, -1, -2. Yeah, so anyways, but these are actually the same thing. Like this is equal to this. It just depends on which point you chose originally for your HK. So that's the main thing. So just remember, HK has to be on the horizontal asymptote, so along this line, and it has to be directly below one of the other points on the graph. So I could have either chose that, which I did, and I got this equation, which is one correct version, or I could have chosen that, and I would have gotten this version. I could have chosen this one. It's just, it would have been a little bit awkward because this is already part of the exponential growth, and usually HK is sort of right in the middle. But I could have used it and it could have worked. It would have given me some variation of this. So anyways, there's a couple of them for you to practice in the homework. And of course, I'll be there on Friday and I can answer any questions you might have.